Welcome everybody on Zoom. Welcome everybody in the lecture hall. Today, we are going to start actually a new phase of the course, because until now, all we've been looking at is how to store data in the cloud, on S3, on Azure Blob Storage, on HDFS, distributed file system. We looked at the data formats, XML, JSON, YAML, Parquet, Avro, CSV, and so on, and many other formats. We looked at the data modeling, trees, parsing denormalized data into trees. We saw that when you validate data with a certain structure, you can actually visualize it as so-called data frames, which are a generalization of relational tables, but where you allow for nested arrays of objects, but in a structured way. Which allows us to take less space and be much faster when reading the data. Plus, when you have a schema, it means that you know how the data looks like before you even look at it, right? Even before reading the data, you already know the keys that you will find in there, and you can optimize a lot. But all of that was only about storing data, creating data, reading data, and so on. And now we can actually start doing the interesting thing, which is to process the data. And the sort of things you can do is actually amazing. This here was the picture of the first black hole that we managed to build. It's not a real photography because we cannot do it, but it was reconstructed with massive computations from observations all over the planet. This was the first one. This is not the one in the center of the Milky Way. This was the one far away. In the meantime, we also got a similar one, but this one was the center of the Milky Way. But this is the sort of things that you can do with massive computations on large clusters, right? Okay, so this is the stack that we had until now, and we've already covered quite a lot, right? It's quite impressive what we've already done until now. And you see that we are moving our way up. Today, we are going to study the processing of data. I have good news for you is that what we've been doing with XML, JSON, modeling, validation, and so on, you can let it sink in and digest a little bit, because today we don't directly build on top of it. We will use HDFS, the notion of blocks, storing data in parallel file systems. But the first framework we look at, MapReduce, is agnostic of the actual formats that you have in there. So you can really take the time to digest everything we've been doing last week and this week. But don't worry, because we will actually assemble the pieces of the puzzle together again, probably next week or the week after that, when we actually will get to query data frames in parallel. And that's going to be awesome, piecing all the puzzle together. All right, but I have an example for you that I like to do. Sometimes we even did it in the classroom, but now we are not so much ahead of time. It's actually great because I answered a lot of questions you had. We used to actually do that directly in the classroom. I would bring some Pokemons, on the printed paper, and hundreds of them, and I'm interested in counting them. What I hunted last weekend, in order to know how many of each I actually caught. If I do it alone, if I just count on my own, it's probably going to take me an hour or a lot of time. And in the classroom, we could actually do it faster. And the secret was to spread this in parallel. So this is what I want at the end. I would like to have the count, so an integer for every one of them. That emerges from the computations. So what we do in order to make that much faster than I could do it on my own is that I split roughly this heap of Pokemons into 8 or 10 packets, right? Randomly, just like that. I just spread them more or less evenly. And then 10 volunteers in the class would take them with them and start counting them. And the task for each one of these 10 students was to count what they have. It's only 10% of the whole amount, right? But to count them and to write on printed paper, you know, for every single Pokemon, there is one of these, 3 of these. I don't know the names. I just know the 4th one is Pikachu. That I know. So basically, you write down how many you have of each, right, for one person. And this is all in parallel in the classroom. Then what happens is that we ask for 8 more volunteers whose task is to kind of merge the whole thing together. And the way that it works is that every one of these persons is assigned 1 or 2, because there's more Pokemon than persons, so 1 or 2, in that case 1, Pikachu. And then there is what is called a shuffle, where the persons who counted the Pokemons have to distribute, they cut the piece of paper Pokemon by Pokemon with scissors. And then the person in charge of Pikachu must get all of the leaflets for a Pikachu. Needless to say, that's a huge mess, that part, because it's like people walking all over the lecture hall trying to find each other and to transmit the Pokemons. But the fact that it's a big mess is actually a feature of teaching, because this is the same in the data center. We'll see this actually happens then in the data center. The shuffling is very, very heavy. In fact, the complexity is quadratic in there, because every one of the phase 1 persons have to meet every one of the phase 2 persons. So quadratic complexity. And so every person in charge of doing the merge is making the additions, right? 1 + 2 + 1 + 3 + 1, which is 8, and writes down the result on a piece of paper. And now, you know, this is the total amounts of Pikachus. There's 8 of them. And at the end, you bring back all of the merged numbers by the second phase helpers, and you get the final results. It was a bit more than that. I just made up these numbers on the slides. It's actually hundreds, but the whole thing more or less happens in 20 minutes, roughly, to do that. So yeah, that's what it is. And in fact, this is MapReduce. This is exactly MapReduce. Who heard of MapReduce? The name? Who never heard of that? Okay. Who knew the name MapReduce but didn't know what it was about? Okay, great. So we'll learn a couple of things today. Well, in fact, this was MapReduce, because this here is actually a map, and this here is a reduce. So now I could almost say, okay, the lecture is done, go back home, that's it for the week, right? But of course, there's a few more interesting things to say about that, and we'll go more into the details and do it a bit more formally, but essentially, this is what this is about. So the idea of MapReduce, of course, it's not real people that actually do it, it's in a data center, so we have a storage level, which typically is HDFS. At least we tend to use HDFS for the textbook example, but it also works with S3, with you know, any other storage layer in the cloud, right? So we have a file system. So what does the data look like on it? So of course, it's not going to just be printed Pokemons, right? It's going to be actual files. So we already looked a little bit into what there is in there. It could be text files, right? Maybe you have the complete works of Sherlock Holmes. This is actually Sherlock Holmes, right? Became public domain a few years ago. This is why there are so many series and movies about it. But you can find the full text online, just a few megabytes. So you could have that stored on HDFS. You could have text, and that can be billions of lines. In fact, this happens in reality for the people interested in indexing text, right, in the context of information retrieval. So you could have huge amounts of documents and books and publications stored as text, and you should imagine billions and billions and billions of lines in your cluster, potentially even trillions, right? But let's imagine billions for now. So this is what you could have, and that we want to process with MapReduce. Here's another example of things we could have. Instead of just text, the text might have a bit more structure. In that case, it's actually CSV, right? So you recognize CSV, but it might be CSV files with billions of lines, right? So in that case, it's both flat and homogeneous, could almost fit in a relational table. Does anybody know what this is? Nobody knows? You recognize the data? Zarsilütte? That's the Springs Festival in Zurich. That's all the years. And the date of Zarsilütte and then the time that it took for the bug to actually completely burn, and you know that indicates whether the summer is going to be warm or is going to be cold. So for those of you who are new in Zurich, don't miss it next April in 2023 in Zurich. That's a whole festival in the city. All right, so these are the times in the third column that it took to completely burn, and then there is the guest content that gets invited. Sometimes it's from another country like Strasbourg. And in 2020, as you all know, it was a bit special, so there was nothing. I put a few nulls. But basically, just to give you an example of the sort of data that we could have in HDFS. Okay, and of course, we've been doing that for billions of years since the start of the universe. So we are looking at billions of lines in there. You also have people that don't necessarily use CSV, but that over-optimize the storage, meaning that if the year you know that there's exactly 4 digits, that you don't need the comma, you know exactly where it stops. So you can save a bit of space by compressing a bit more in there, putting zeros instead of nulls and so on. In fact, people doing that, for example, are the weather people, weather and climate. They have that kind of formats where the weather stations save data in that form, and then you know exactly which characters on which line correspond to what. So this is a bit more raw, but this is also the sort of things that you find, right? So not necessarily CSV. Another way of structuring the data, if you're just interested in the years and duration, is an explicit key value model, right? So in that case, we have the year as the key, and we have the time that it takes for the bug to burn completely, right? So in that case, it's a key value model. How do we know there is the space? You see that there is a special character, in that case, a space right here that separates the key here from the value there. You could also have stored in JSON, right? You know JSON, so JSON lines is actually quite a popular format to store data in. So you have one JSON object on every line, and then you have billions of them. We'll have data sets like that. The Great Language Game, for example, is a data set stored in that format. It has, I think, 16 million of JSON objects like that. So you see here, it's flat. It's not homogeneous because you see in the year 2020, we don't have all the fields, so it's not completely homogeneous, but it is flat. All right. Okay, as it turns out, in 1923, there was also something different. Okay, then we have binary files. We could also store maybe Parquet or whatever format. So in that case, just zeros and ones. Of course, we could have petabytes of that, but as you know, HDFS is splitting that into blocks. So it's actually 128 megabytes at the same time. There is a special kind of file actually that was kind of created with MapReduce that is called a sequence file. This sequence file is just a binary format that stores key values, but in a binary form. Now you're going to tell me, okay, we've already seen that. We've seen that with H files in HBase. Yes, but that's not exactly the same thing because in HBase, the H files are sorted by key. Not in that case. In that case, it's just a list, doesn't need to be sorted. It's just key values in any format. It is a native format for Hadoop for storing key values. Why? Because as we will shortly see, Hadoop MapReduce processes key values. The only thing it processes is key values. It doesn't know anything else than key values. You know, like if you have a hammer, you see the world as a nail. Well, for MapReduce, everything is a collection of key values, right? So this is why we have this specific format that is also there to store things as key values. So for example, you could store, which one was this one? For example, you could store as a sequence file instead of just text, right? Like this. Okay, now this is something that I already told you about, is that typically you don't have a single file of a billion of lines. Typically you have shards of the files. So you have maybe 100 or 1,000 files. And these files are typically a few gigabytes in size, so they are themselves split into blocks, right? But it's actually rare that you would have one single enormous file in HDFS. Rather, you will have 100 or 1,000 files, and very often they have a naming scheme that they are literally numbered, like part 1, part 2, part 3, with even heading zeros. Okay. Now, what's also nice is that we saw that instead of storing data directly in HDFS or in S3 or in Azure Blob Storage or Google Cloud and so on, we also looked at an alternative way of storing it, which is HBase, right? What do we get with HBase? We get that we can update the data easily and we can have much lower latency, right? But HBase is also a storage level, right? We saw it doesn't have the full flexibility of a relational database, right? So, but it still organizes the data in table. And you could, for example, store it, using small values in tables like that, even though for that, probably a relational database will do just as well. But typically what people like to do with HBase is that they actually store XML and JSON objects, one object per cell or one XML document per cell. It's also a quite common way of using HBase. Some people also put HTML in documents in the cells. So you could have, for example, here an HBase table, and on every cell in some column, you just have the data stored as one XML elements or document every time. And by the way, you could still have a schema. Now you know the schemas, right? So this could be a schema for the data that we are storing right there in XML that stores that data, right? Okay, so this is just to make you aware that no matter how the data is stored as text, as JSON, in HBase, as XML, and so on, we are now going to process that. How? In parallel, because since the data is cut into blocks, in HDFS, we can process the blocks on the machines of our cluster. And in fact, I love to make the comparison with this because this is pretty much what we do with data in order to query it, right? Okay, so now let's move on to the query itself and try to think on a very high and abstract level. What is a query? A query is something that for now is a black box that takes some input data, a collection with billions of items, billions of rows, billions of JSON objects. So it takes some input data and it creates some output data, right? This is pretty much what a query does. But here I just put a black box, right? This might be billions here and billions there, and we need to execute that query. By the way, the output data will be back to HDFS or on S3 or in HBase or wherever you want, right? You can even read from HDFS and write back to S3, or you can read from S3 and write back to HBase, right? Any combination is possible, right? Okay. So now, what is the idea behind MapReduce? The idea is that the data that you look at, the input and the output, are typically sharded, organized in blocks, chunks, splits, no matter what you call them. In the case of MapReduce, we like to call them splits, so I'm going to use the word split. So the data is split here, one split, one split, one split, one split in the input, and we will also output it in splits, right? Now, this here is the Christmas wish that we have. Imagine that the query is such that every shard of the output can be created just looking at one split in the input, right? Then I can take the first split, I can just execute the query on one machine, and then I can output the final result here as a file on HDFS. On another machine, I can look at another split that might be an HDFS block sitting on some other machine, and on that machine, I execute the query and I write back again a file to HDFS, right? On a third machine, and this is all in parallel, I can look again at another HDFS block that is a split for MapReduce, execute my query locally, and then output as a file to HDFS. When you output as a file to HDFS, it will create locally a replica of each blocks, and then the second and third blocks go to other machines, right? But imagine here that we have 8 machines in our cluster, and we have one block on each machine. I'm oversimplifying, right? Then each machine can just take the block it has, execute the query, and write back to HDFS. Who understands that this is very efficient and it's going to be faster than on just one machine, right? Okay. Now the problem is that this is not reality. In reality, this is not how the queries actually are. In reality, this is more like how it is, right? A big spaghetti. With the idea here that, for example, in order to create that shard of data right there, I need to look at every single split in there. So I need the entire input data in order to create the data there. Then that doesn't work. You can no longer do that, right? So this is actually the real life thing. And especially if you start having to aggregate data, then this is what it's going to look like. Now, does that mean that everything is lost and there is no hope that we can ever execute that spaghetti in an efficient manner because it's just all over the place? Well, actually not, because in the typical case, it's not quite like that. It's not quite like this, of course, but it's also not quite like that. In the typical case, it's more like this, that there is a bit of structure here and there. It's still globally going in all directions, but locally you do have a bit of structure. And in fact, if you observe, you can zoom in at some places and observe that at that place of the query, things are going in parallel, right? And at that other place, thing is going in spaghetti, right? So this is what we call the shuffling, right? So we're going to have a bit of both in a typical use case. Well, the insight of MapReduce is that if it is indeed the case that looking at your query, there is a bit of this and there is a bit of that, then MapReduce is for you. And as it turns out, it is very, very often the case that you recognize these patterns. So this is MapReduce. It is a very simple assumption that your query can be executed as a first phase with plenty of queries in parallel. This is called maps, right? And here, this part right there is exactly as we described here, right? It's all going in parallel on different machines. Followed by the huge shuffle where it's all over the place, right? Quadratic complexity. Followed by another phase where things go in parallel again, which we call reduce. Why reduce? Because remember with the Pokemon, this is where you get plenty of sheets of paper with the same key, and then you sum them up to a single one. So you reduce the Pokemons. All right. So map reduce. In fact, I like to say that it should be called map shuffle reduce for pedagogical purposes, because people tend to forget that there is a shuffle in the middle, but it's called just map reduce, right? Just do not underestimate the complexity of the shuffling in the middle. For whom is that clear? Right? This is MapReduce. Okay. Now, I'm going to make this explicit because what you shuffle in there is not anything. This is intermediate data that you shuffle. It's basically the output of the maps that you shuffle around and send over as the input to the reduce, right? So this is going to go, as you can guess, in the cluster over the network, right? Over the network cables between the machines, between the nodes, between the racks. Okay. All right. And the reason why the shuffling is actually taking some time is that there is network bandwidth, right? And you have limited network bandwidth. The amount of bits that you can send all over the place is limited. All right. What is incredibly surprising is the enormous amount of use cases that something as simple as that actually covers. It is extremely impressive how powerful that thing is. And if it does not, it's not a problem either, because then you can just execute several of these sequentially. You have MapReduce, then you have another MapReduce, then you have another MapReduce, then you have another MapReduce, right? Even something like matrix multiplication can be done with a sequence of MapReduce, right? Which in machine learning is actually very useful, right? You know that in machine learning hardware, all you do is plus and times, right? It's just addition and multiplication in there, but massively efficient. Okay, now, I will tell you more about this data that we shuffle around, even though this is actually not new because I kind of already told you. Everything there is a collection of key value pairs. Absolutely everything. Collection of key value pairs here, collection of key value pairs in the intermediate data that gets shuffled around, collection of key value pairs in the output. What's very important is that I'm not requiring these key value pairs to be ordered, right? Ordering key value pairs was really just in HBase when we create these H files with the log structured merge trees, right? So we have key value pairs all over the place in here. Now, what about the types of the keys and the types of the values, right? Can we have some structure in there? Well, yes. In fact, we do have a type of key and a type of value in the input. We have a potentially different type of key and type of value in the intermediate data. Doesn't need to be the same type as the input. And we have yet a third type of key and type of value for the output. An example could be that, for example, the input is the key is an integer and the value is a string. Maybe in the intermediate data, the key is a date and the value is a JSON object. And maybe in the output, the key, I don't know, is a string and the value is going to be some XML elements. Right? I'm just randomly throwing things around here, but this is the idea. Okay, so key values, key values, key values. Now, very, very often, the intermediate types are the same as the output types. Right, so I would say in 80% of the cases, that's the case. Doesn't have to be, but in 80% of the cases, you do have the same type here and there. In fact, what happens in the reduce phase then is that you just take all of the key values of the intermediate data that have the same key, and you aggregate all of the values that are associated with that key into a single one, and then you get an aggregated key value in the output. So that's the reason why it's very commonly like that, right? Okay. So now I'm going to walk you through again through MapReduce, but now on a bit more abstract way than the Pokemons and given what I've shown you right here. So what is going to happen on the logical level with MapReduce? Well, first, we start with map. So what happens is that we have our input right there. So this is on HDFS, on S3, in HBase, in a relational database, wherever you want it to be. And we have billions of key values. Yes, I'm assuming that these are key values. As you saw earlier, it wasn't always key values. You had text, you had JSON objects, and so on. We'll worry about that later. How do we hit it hard enough with a hammer to turn all the input in key values? We'll see later. For now, I assume that the input is made of key values like that. So the first thing we do on the logical level is splitting, right? So these billions of key value pairs, they are split in partitions like that. Note that this is logical. In practice, you don't need to do it. It's already done. HDFS already splits the input, right? Because it's already organized in blocks. So this whole thing, if you look at it logically on HDFS, is actually stored one block, one block, one block, and so on. So that's how it already is on HDFS, right? But logically, we split the input like that. Next, what's going to happen is that we take each one of these key values in the input, and we apply a map function. It's just a mathematical function that takes the key value and outputs 0, 1, or more intermediate key values, right? What function is that? Well, that's the user who decides. It's you, user of MapReduce, right? So you provide the map function to MapReduce, and that function is supposed to take a key value and outputs 0, 1, or more intermediate key values. Okay. Now, as you can imagine, this is done here one by one on each key value, but what's going to happen is that each split will be processed together, right? So you basically, in the first split, maybe on one machine, you apply the map function to each one of the key values, then you get when you put them all together, all the intermediate key values that the function calls gave you. Then you have the second split that you call the function on 2 key values, and then you put together all the intermediate key values. By the way, in that case, probably this one or this one generated 0 intermediate key values and the other one just 1. So this is why you have just 1 here. And then you again have another split with key values. You apply the map function to each one of them and get an intermediate partition right there. Okay, who is following? Okay. Next, this is all on the logical level, right? This is not done physically, but just for you to understand on the logical level, what happens is that all of these intermediate partitions of key values, think of them as all going together. Now we have a huge collection of intermediate key values that you look at it together, and it's not ordered in any way, right? But let's order it logically. Again, physically, you don't have to, but logically in your head, imagine that you sort all of these intermediate key values that you've generated over the entire cluster, everything. So you sort them. So there's plenty of key values with key 1, then there's plenty of key values with key 2, then plenty of key values with key 3, and so on. Next, partition it again, but this time by key. So you have all the key values with key 1, all the key values with key 2, all the key values with key 3, and so on, right? So again, I repeat, you had these unordered intermediate key value pairs all over the place, put them all together, sort it logically, and then partition it by key. So you have all the key ones, all the key twos, all the key threes, and so on. Next, you apply the reduce function to each one of these partitions right there. So here we have key one, key one, key one, and you call the reduce function on these key values where the key was key one, and you get 0, 1 or more output key values. In that case, just 1, but 0, 1 or more in general. What's very important to understand is that what you have here on the left is everything in the intermediate data that has this key. You have everything. There is no other key value with key 1 that you would be missing. Everything has to be there. This is why the shuffling is actually important. So all the key values with key 1 are in here, and you call the reduce function on all of that together and get the this 0, 1 or more output key values. Now I'm showing the same thing again in the case, because I told you it's very often the case that the intermediate types of the key and the value are the same as the output types. So in that case, you typically keep the key. So if you had all the key values with key A and you reduce, typically you will also use key A in your output. Typically, you will output exactly 1. Then the value is whatever aggregation you get from ABC. Could be the sum, could be the count, could be the average, could be the mean, the max, percentiles, whatever you want to compute. Okay. Now, this is just to make clear that generically I said 0, 1 or more. So you could have 0, you could have 1, you could have 2, you could have any number you want. It's just that in general, it's just 1 in 80% of the cases. Okay, so this reduce function, of course, has to be called for every partition of the intermediate data, right? So it's called for key 1, it's called for key 2, it's called for key 3, and so on, right? Okay, so now if I put everything on a single slide, that's pretty much what happens, right? We have the input data over there. That is a collection of key values, partitioned naturally on HDFS as blocks and so on. Each block from the perspective of MapReduce is called a split. Every split is processed by calling the map function on every key value, and we create intermediate key values, right? So every split will create plenty of intermediate key values. Then we put it all together and sort by key. Then we partition again so that the keys that are the same are together. And then you call the reduce function for every group of key values with the same key, right? Okay, and then you get the output data. For whom is that clear? All right. Okay, now that was the logical walkthrough, right? So this is how things happen on the logical level. But now you're probably eager to know what actually happens on the cluster of machines. So, as I said, MapReduce runs on the local file system, on HDFS, on S3, on Azure Blob Storage, on HBase, anything you want. Here I put Hadoop MapReduce. What do I mean? It's the open source version of MapReduce. There is also the Google version, that the original one was also called MapReduce, but in Hadoop it was re-implemented open source. And so in Hadoop you have HDFS, HBase, and MapReduce. These are all part of Hadoop. Okay. Now, typically, when you apply MapReduce, you might have terabytes of data, you might even have petabytes of data, and you can potentially have thousands of nodes, an entire cluster, an entire room in a data center with thousands of nodes, and all of that goes in parallel that you map in parallel on all these 1,000 machines. Then you shuffle data around, imagine the complexity of that for 1,000 machines being quadratic, and then you reduce again in parallel on the machines, and write it back to HDFS or any other storage backend. Now, I have good news for you because this is going to be easy to learn, is that the architecture is nothing new compared to what we've seen before, because in HDFS, we saw that it's a centralized architecture where the coordinator node is called the name node and the worker nodes are called data nodes, right? So this is HDFS. In HBase, we saw that the coordinator nodes are called HMaster and the worker nodes are called region servers. Well, guess what? For MapReduce, it's all over the same architecture. Again, we just need to learn a new name, which is job tracker for the coordinator node and task tracker for the worker nodes. Okay, so you just need to learn these two names, job tracker, task tracker. All right. Now, just to make clear, these are the same machines. Every time we abuse, as I said, when we say name node, data node, we abuse that by saying the machine, the data node machine, the name node machine, but these are really processes running on the machines. So you have to imagine that on the coordinator node, you have a name node process plus an HMaster process plus a job tracker process on the same machine. And on every worker node, you have the data node process plus the region server process plus the task tracker process running on the same machines, right? Okay, just to be clear, this is version 1 of MapReduce, with which I'm starting. There is actually a version 2 that made it even better, but we need to start somewhere. So I'm starting with this simple case where we have the job trackers and the task trackers. Okay, and as you can imagine, the fact that it's running on the same machines is a huge plus for the performance of our system, because the data nodes process and the task tracker process are on the same machine. That means that when you execute your map function on the input, where is the input? It's on the local disk of the same machine. It's exactly this idea of short-circuiting with HBase that we already had. You can also short-circuit with MapReduce. This is called, there is a name for that. It was kind of a hype 10 or 15 years ago. It's bring the query to the data. You bring the query to the data. That means that where is the data? It's sitting on the worker nodes here with the data nodes processes. Where should you query it? Well, on the same machines. So you just bring the query there and execute the query on the same machine where the data is actually physically. So this is bring the query to the data. So now you can imagine that we have the data in there. It is all made of blocks, and we have replicas. There's 3 replicas of each blocks all over the cluster, but let's focus on one of these replicas. So I'm only showing one replica of each block, and I'm showing the machines on which it is. I'm also putting splits there. Split is just the MapReduce name for what corresponds to a block, right? It's the set of records that are on the same block. So here you have 2 splits here, 1 split here, 1 here, 1 here, 2 here, and 1 here. And of course, the entire file, you know, because of the name node, that the file is the sequence of all these blocks. But now, what's going to happen is that on the same machines where you have these splits stored on the local disk, we are going to create these map and these reduce processes, right, on the same machine. That's basically part of what the task tracker is doing. So the task tracker is going to execute the map function for all the key values in that split and all in that split. So I put 2 little m's here for map. More exactly, these would be threads, right? So this, if I oversimplify, this would be a process, the task tracker, and then you have threads within the process, and each thread is looking at one split, right? So here we have 2 threads, each looking at their splits. Here we have 1 thread, 1 thread, 1 thread, 2 threads here looking at these 2 splits, and here nothing, right? Okay, maybe extraterrestrials trying to communicate with us. Okay, sometimes the collocation is not possible. So it might be that here you have a map thread here that is actually reading the data from a different node. That's okay, it's just going to be a bit slower, right? Instead of a local read, you just go over the network in order to get the block, right? And this is fine. Okay. And then at the end, you have the reduce task. So there's the big shuffling around, where you shuffle the data around, and then you process the reduce function in parallel as well. What is important is that I will come back later, probably next week, on the details of that. But a fancy name that we have for these threads here is that we call them slots. Right, so split is the MapReduce name for the key values in a block, and slot is the MapReduce name for the threads that process each one of the splits. Is there a question? Yeah.
Why does some node have multiple threads for reduce?
Oh, it's just it can be multiple per node. It's a bit random. It's basically load balancing. You just try to load balance over the cluster, and some machines will have more, some machines will have less. Right? It's the same for maps actually. If you notice, some machines have more maps than others. This is really just load balancing. This is all configurable. The user can actually say how many reduce slots they want, right? This is something you can control. Okay. Okay. Still have a few minutes. I can end with this thing, actually making a connection with HBase, as you will see. Now, let's imagine we start processing the data. So we have all of these map slots that process the data reading from the splits, reading from the local replicas of the block. And imagine that we produce these intermediate key value pairs, but at some point the memory becomes full, right? There are so many key value pairs we generated that it doesn't even fit in memory anymore. What do we do? It's written in there actually, but can somebody give me a different word than spill that we've seen before? Yes? Flush. And another word? You flush and then you compact. Exactly. Well, it's kind of the same idea, because everything we've learned now in HBase, you can get it for free here, because what's going to happen is that when you have too many intermediate key value pairs in memory, you just flush them to disk. You, in fact, sort them, but this is really just for efficiency, because if you sorted them, it's easier to do the shuffling later. So we flush them, sorted to the disk. If we start having too many of these files, we can also compact them. Don't have to, but you can, yes? Oh, there's an assumption they do. Right? If you really generate so many that it doesn't fit on the local disk, then the whole thing would probably fail. And then you just need, as a user, to reconfigure the cluster, either simplify your query or maybe add more machines in order for this not to happen. Right? So to be clear, it can exceed the memory, but if you start exceeding the disk, then you have a problem and you need to find another way. Right? So indeed, this is, thank you for making it explicit. There is the assumption that it's going to fit on the disk. Because again, this is the local disk here. It's not HDFS, right? In HBase, that would be HDFS. Here it's just the local disk. Okay, and you can have the same sort of things. Even though I think it's probably to a lesser extent than HBase, right? In HBase, you have a heavy log structure merge tree. In the case of MapReduce, you probably will not go that far in the level, right? So many times you won't even need to flush. And sometimes all you need to do is flush and you don't even need to compact, right? But technically you have the theory to even handle larger amounts, okay? Then you shuffle things around. Once you're done, it's all stored in memory, or if you flushed, on the local drives. And what happens is that in order to flush, the reduce slots are connecting over HTTP to all of the nodes and requesting the key value pairs that they are responsible of. For example, they say, okay, hello, I'm responsible for key A. Please give me all the key value pairs with key A. And since I told you that when you have it in memory or when you flush, it's all sorted, then you can imagine that for every map slot, it's super easy to deliver these key values because it's all sorted. So just look them up in the sorted order, and then you transmit them over HTTP to the reduce slots. So of course, I only talked about one value, but now imagine thousands of reduce slots talking to thousands of map slots and all the HTTP connections that you need for that, right? So this is going to take a while. Do we have a question in Zoom?
Yeah, does MapReduce query pre-processing, query optimization like in RDBMS, or user have to optimize how they query?
To some extent, yes, that is exposed to the user. I'll talk about that next week. There are optimizations technique, but it doesn't go as far as an RDBMS. You basically get these optimizations on additional layers on top that we will study actually in the coming weeks, by the way. Right? This is very physical. Here we are looking at a physical level, it's very low level, very simple, but very powerful. Okay. I think it's now the time, yeah, 58. So let me just check that you followed. I need to go my way again. Just a few more seconds so that I can open that question. There you go. Here you go. So just checking that everybody followed and I didn't lose you. That looks good. Okay, that looks rather good. Okay, so thank you very much, everybody. Enjoy the exercises, and I'll see you next week for the continuation of MapReduce. Thank you.